In 7.5, we're going to be talking about a topic that's called rationalizing denominators, and then later on we'll rationalize numerators. What rationalizing denominator is basically if you see a square root or any root in or radical in the denominator, you are going to try to get rid of that radical. The reason why we do this is it kind of goes back to how things were done without calculators. If we were to try to set this up as a long division problem, you see that we have a radical in the denominator. So you would set this up, long division, and numerator would go underneath, and we would put the square root of 2 on the outside. Well, the square root of 2 is an irrational number, which means it goes on forever, which is about 1.4114. But the thing is, because it's irrational, it goes on forever. It never ends. So when you're dividing, or when you try to divide, you really don't know exactly how many times this number goes into 4.00000 because this square root of 2 never ends. So what rationalizing the denominator does is we're going to multiply by square root of 2. And this is really 1, so it doesn't change anything. So it's 4 square root of 2 over 2. Now this actually reduces, but it's because now the 2 is on the outside, where the 4 square root of 2 is underneath. And even though this part's irrational, it goes on forever, it being 5.656, you're at least to know how many times 2 goes into 5, and then the 6, and the 5, and the 6, and so on, so that you can actually start dividing it longhand. So how do we do this rationalizing the denominator? Well, you're going to look at the radical that's in the denominator, and you need to look at the index. And if we look at number 1, the index is 2, it's the square root, and it's the square root of 2. There's a couple ways that you can think about this. You can think about what you need to multiply the denominator by in order to get a perfect square. Or you can simply multiply it by the same number depending on how many or what the index is. So since the index is 2, zoom in a little bit, is 2, I want to multiply by the square root of 2. That gives me a pair. I'm going to do square root of 2 over 2 because that will give us 1 and won't change the problem. So when I go to multiply this, I'm going to get 7 square root of 2. Remember, you can't multiply something inside a radical with something outside the radical. And then because it's a square root and a square root, they're going to cancel each other out, and it's going to be 2. Remember, 2 times 2 is 4, so it's the square root of 4, and that gives you 2. Now, you should always check to see if the 7 and the 2 right here cancel, but they don't, so that's going to be our answer. We're going to look at number 2 now. You'll notice there's 2 radicals, square root of 9, square root of 16y. What I'm going to do in this case is I'm going to simplify those radicals first, make it a little bit easier to work with. The square root of 9 becomes 3, square root of 16 becomes 4, but the y still stays underneath. Now this is a little bit harder because we don't know what to multiply to get a perfect square number. So this is where the index comes in. The index is 2. That means I need at least 2 y's in order to pull out from this radical. So I'm going to multiply by the square root of y over the square root of y. What that does is it makes the denominator square root of y squared, which will go in evenly, so it'll be 4y. Now my numerator will be 6 square root of y. Oops. And that doesn't reduce, so we leave that there. But the 6 and the 4 does, So it'll become 3 over 2. Keep the y. And remember, square root of y over y doesn't cancel because you can't cancel something that's in a square root. So, final answer is 3 square root of 2 over 2y. Number 3 is a little bit different. We have the cube root of 2 over 25. So like in previous lessons, we're going to take the cube root, apply it to the numerator, and apply it to the denominator. Now this is a little bit different because I just can't multiply it by square root or even cube root of 25, because that's the cube root of 50. Sorry, that's 625. 25 times 25 is 625. And that's not a perfect cube. So we're going to have to back up a little bit. What you're going to do is, because we're looking for a perfect cube, is we need to kind of go to our hopefully handy list of perfect cube numbers. So remember, I told you this previously, it's always useful to have this list when you're looking at numbers. So 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216. And we'll stop there, and you'll kind of get where I'm going with this. So what I'm trying to do is I'm going to see if there's any way that I can take this 25 and multiply it by a whole number to get me a number on the list. Well, it won't go into 28, it won't go into 27 evenly, or 24, but it will go into 125. And it goes in 3 times. So I'm going to multiply by the cube root of 3. And what that does is it makes the denominator 125, which the cube root of 125 is 5. Now the top we can multiply because it's the same index, cube root of 6, and that doesn't simplify, so we can leave that the way it is. The next thing we're going to talk about in this section is conjugates. And we've actually seen conjugates when we talked about the sum and differences of two squares or dots problems. Remember back when we had a plus b, a minus b, and we would FOIL that, and basically we'd end up with a squared minus b squared, because when you would FOIL, those outer and middle terms would cancel out. Well, what a conjugate is basically this right here. It's where you have a binomial that's pretty much the same, A-B format, but one's positive, one's negative. So how does that help us when we're talking about rationalizing denominators? Well, not all denominators are going to have monomials in the denominator. Some are going to have binomials, like this one does in number 4. And what a conjugate does is it allows us to cancel out those middle terms like we talked about, and it actually then gets rid of the square root. Here we have a conjugate, and you'll remember this from dots. Conjugates have this format a plus b, a minus b, where the a and the b are going to be the same, but what the difference is the plus and the minus. And if you remember back to FOILing, why that happens is because the outer and the middle terms cancel out, so we're left with just 2 terms, which are squared. Now, how does this help us with binomials or conjugates and rationalizing them? Well, because not everything has a monomial in the denominator. Some have binomials. If we're trying to get rid of a radical that has a binomial, you're going to use the conjugate. So what you're going to do is you're going to look at the denominator, and you're going to take the conjugate of it. So in this case, it would be 2 square root of 5 minus 1. And I do that for numerator and denominator, because really what I want to do is be multiplying by 1. That's what that is right there. So What's going to happen is I will multiply the numerator just as normal, distribute the 3 to each term. So I'll get 6 square root of 5 minus 3. And then I will FOIL the denominator. Now, when I FOIL this, you'll notice that it's going to be like a dots problem. I'll get 4 times square root of 25, which will really, that'd be 20. I'll do the outer, which is minus 2 square root of 5. The inner, plus 2 square root of 5. And finally the last, which would be minus 1. What should always happen in this with the conjugates is the middle terms cancel out. And because this is squared, your first term and your last term will not have any radicals in it. So my answer will be 6 square root of 5 minus 3 over 19. You would do the same thing if it had multiple square roots with the binomial. The conjugate in this case will be square root of 3 plus square root of 2. I would do that for the numerator and the denominator. Now in this case, though, this is another binomial, which means that we have to FOIL. So we're going to FOIL the numerator, get square root of 15 plus square root of 10 plus 3 square root of 3 plus 3 square root of 2. Notice nothing in the numerator are like terms, so we're going to leave those. Now, we can FOIL the denominator, that's fine, but remember that those middle terms will always cancel out. So we'll get square root of 3 times square root of 3, which is square root of 9, which is 3. And then I'll get square root of 2 times square root of 2, which is square root of 4, which is times 2. So it's really minus 2. This becomes 1, and then anything over 1 is itself. So this long numerator is actually what we end up with. And finally, our last objective for the day, rationalizing the numerator. It's the same concept except you're going to get the radical out of the numerator. You would probably do this in the case of like terms if you're adding fractions. So what you're going to do is you're going to simplify the numerator, or simplify the radicals just as you would any other time. So square root of 9, square root of 2, square root of 25, square root of 3. And that becomes 3 square root of 2 over 5 square root of 3. Now I'm trying to rationalize the numerator, which means that I want to get rid of the square root of 2. So now I want to multiply square root of 2 over square root of 2. And that gives you 3 times 2 over 5 times square root of 6, which is 6 over 5 square root of 6. Again, we can't cancel those out because one's underneath and one's not. And again, this is rationalizing the numerator, which would be something to do if we're adding and subtracting fractions.